Faz um teste faz o teste da apresentação primeiro, antes do stream. Vai ser em inglês, né? É isso?
Vocês sabem, eu preparei em inglês, vocês
não pode
preferirem, não pode ser. Para mim é mais fácil português, mas eu posso também apresentar em inglês.
Tem alguns alunos que são de fora também, Helder.
Ótimo. Então, tá bom.
Eu acho que eles não falam em português ainda, né? Eu sei.
Certo. Então, deixa eu tentar compartilhar minha tela aqui, só para ver se está tudo ok. Vocês conseguem ver aí?
Eu consigo.
Ótimo. Então, quando puder começar,
só não está ainda em modo apresentação, né?
Isso, ainda não está.
Tá bom.
Vamos colocar aqui já. Modo apresentação.
Então, eu vou fazer uma pequena introdução. Eu peguei das informações do teu currículo Lattes, Helder.
Perfeito.
Só para anunciar para os colegas também terem um pouco de... So, I'm Luiz Eduardo Antunes Vieira, researcher from the Brazilian National Institute for Space Research, and I would like to welcome you to our heliophysics and spatial physics seminars, which is promoted by our institute, the Brazilian National Institute for Space Research. In particular, this seminar is being hosted by the Spatial Physics postgraduate program and by the Researching Heliophysics project, which is part of our internationalization effort going on at our institute, which is also sponsored by CAPES funding agency. Our guest today is Dr. José Helder Severo from the Plasma Physics Laboratory at the University of São Paulo. Dr. Severo graduated in physics in 1994 at the Russian People's Friendship University. He has also the master at the same institution in physics, also in 1996. And in 2003, he concluded his PhD in physics at the University of São Paulo. He is currently in charge of the Plasma Physics Laboratory at USP and for the optical diagnosis of the tokamak. In order to unite specialists and train people with expertise in optical design, in 2014, he created a group in optical designers at the University of São Paulo. He has also experience in physics, which is with emphasis in plasma physics and magnetic confinement systems. He works mainly in the areas of plasma spectroscopy, optical diagnosis for nuclear fusion, and optical design. So on behalf of INPE, I would like to thank Dr. Severo for accepting our invitation to present the seminar on spectroscopy of thermonuclear plasmas. We ask the audience to mute their microphones during the presentation, and I think that it's nice to keep on the video, so Dr. Severo will not be alone here. You can ask questions at the end, or if you prefer, you can write down in the chat. So, Dr. Severo, thank you very much.
Okay, thank you, Luis, for opportunity. So, in my presentation, I will give you a short introduction to experimental plasma fusion spectroscopy. Since my talk is about spectroscopy of plasma fusion, I would like to say some words about thermonuclear plasma fusion, but my talk should be concentrated in the radiation and its measurements. In the end of my presentation, I will briefly pass through spectroscope instruments and the optical design. So you know there are two types of nuclear reaction. One of each is nuclear fusion. So this reaction consists of two light elements that unite to form a heavier element. The fusion is the most important process of obtaining energy in the universe. However, to take fusion, two ingredients are needed, that is confinement and the temperature. In the star, the gravitational force is responsible for confinement and temperature because of compression of plasma. In laboratory, the confinement should be obtained by magnetic field, and the heat should be obtained by electrical current, by Joule effect. There are more than 80 types of fusion reaction. However, the most attractive is the deuterium-tritium reaction. Because this reaction has the higher cross-section. So you can obtain this reaction with lower temperature or lower temperature. In this reaction, after fusion of this deuterium-tritium, that are two isotopes of hydrogen, we obtain a helium and one neutron with energy about 13 MeV. One can ask, where from this energy? This energy from, if you analyze the mass of elements before the reaction and the mass of elements after reaction, this mass is not equal. This difference of mass is converted into energy. In the reactor, the kinetic energy of neutron should be transformed in the electrical energy. There are two types of magnetic confinement for plasma. One of which is linear confinement, and the other has a toroidal geometry. Tokamak is a Russian invention that is used to reach and confine the plasma. Of course, the most attractive geometry are those that has toroidal geometry. So the tokamak has the main parameter of tokamak are major radius, minor radius, toroidal magnetic field, and the plasma current. In Brazil, there are three tokamaks. One TCRBR that is located in University of São Paulo. It's a small machine. The major radius of this tokamak is about 61 centimeters. Minor radius 18 centimeters. Toroidal field about 1 Tesla. Plasma current about 100 kiloampere. There is also ET in INPE, also a small tokamak. However, this tokamak has a different geometry. And the tokamak Nova that worked for a long time at the University of Campinas and now is transporting to Espírito Santo. So the density of plasma is very low. The density of thermonuclear plasma is very low. It can be reached at 10 to 20 particles per meter cubic. That is about 1,000 less than density of air. However, the temperature is very high. The temperature of thermonuclear plasma can be reached more than 100 million of degrees. So measurement of plasma parameters is very complicated task. So you need sophisticated measurements involving all areas of the physics, redundant measurements are required, complex tasks involving heavy hardware, and high qualified engineers. One question is, how can one measure the plasma parameters? The most common possible is from the radiation of plasma. Radiation of plasma, there are a lot of information about this plasma. So measuring this radiation, one can obtain a lot of information about this plasma. However, this radiation covers a wide spectral range that is from soft X-ray to microwave. Atoms and ions in the plasma are constant source of radiation. Direct measurements of this radiation give us an enormous possibility to obtain plasma parameters. However, this information is not punctual, but this average along the line of sight. The quantity of interest in spectroscopy measurement is the coefficient emission that is called emissivity. The emissivity of plasma is function of radius. However, when you measure this emissivity, you obtain not emissivity of plasma, but the integral of emissivity. So suppose you have here one detector to measure the emissivity of plasma. This information is not the profile of emissivity. All plasma parameter has some kind of profiles. And you obtain the average along the line of sight. If you have done, if you have good calibration, you can obtain the information about any parameters of plasma, like temperature, density, and so on. One can ask how one can obtain the plasma parameters. The most common measurement of plasma profile is by measurements the line of sight for different positions. Suppose you have a lot of detector and you measure this emission in different position of plasma column. After this measurement, you receive the transversal profile of plasma emission that is called radiance or brightness. Now, after mathematical transformation, you can obtain the profile of this plasma, the emissivity of plasma, that now is function of radius. However, this is kind of measurements is very similar to the tomography. If you have cylindrical symmetry, you can apply the Abel transform to obtain the emissivity. However, this mathematical transformation is not so easy because these will pose a problem. So there are another type of diagnostic where you can obtain the profile of the plasma radiation. Suppose we have here detectors that measure the radiance of plasma from different hordes. And here you have a beam of atoms or light. Suppose so that beam, when penetrate in the plasma, some atom reaction should be can happen, and your detector can register this process. So when your detector registration this process, you know that information coming from this point. So if you have a lot of detector, you can obtain the profile of this radiation. One example of this kind of measurement is the measurement of hydrogen neutral plasma density. In this kind of diagnostic, we have a Ruby laser that's coming through the plasma. When the laser comes through the plasma, the acetate state of hydrogen can be ionized, and if you are measuring the H-alpha emission from the plasma, after the laser passes through the plasma, this emission should be decreased. Measuring this decrease, you can obtain information about neutral plasma density in different positions of plasma column. Spectroscopy is an important kind. The light emitted by plasma can be used to obtain a lot of plasma parameters like plasma density, electron density, ion temperature, and the Doppler shift. There are two types of radiation. One is continuous, that is composed of Bremsstrahlung and the recombination radiation. Another is discrete radiation that are related with emission of spectral lines. For long wavelength, here you have the continuous radiation from the plasma with some level of impurity. For long wavelength, you can see from this picture that the radiation of blackboard in the plasma radiation is very similar. So suppose you can approximate radiation of your plasma by blackboard radiation and use the Wien laws. You can obtain the maximum of emission of plasma for different temperatures. For example, for 170 eV, the maximum of radiation is about 3.65 nanometers that are in the soft X-ray region of the spectrum. It's very complicated to measure any kind of parameter in this part of spectrum. You cannot use the common optical instruments like glass, lens, and so on, optical fiber. So recombination for long wavelength become negligible. Bremsstrahlung emission for hydrogen has some dependence with the plasma density and the temperature. If you have in this plasma, impurity, this expression for emissivity of plasma is more complicated. However, this expression you can rewrite in this form, that are emission coefficient, emissivity of hydrogen, and the average charge of the plasma. If you have plasma only, if you have the hydrogen plasma, this average charge should be equal to 1 because there are impurity in the plasma. This number is higher than 1. In our tokamak should be between 3 and 4. So for high density, the plasma becomes optically thick, and for long wavelength, the emission corresponds to the blackboard emission. For short wavelength, the Bremsstrahlung and the recombination radiation has the exponential dependence on temperature. So measuring the slope of this curve, you can obtain information about temperature of plasma. However, to calculate, to interpret the radiation from plasma, it's a very complicated task. You should know the charge distribution, population density of stated levels, occupancy and density of rates of energy levels, ionization rate, recombination rate, and so on. There are three types of model to describe the emission of plasma. The more simple model is the coronal model that is valid for low density. In this model, ionization and excitation occur through the collision with electrons. Ionization is balanced by recombination, excitation is balanced by spontaneous decay. There is also a local thermodynamic equilibrium model that is valid for high density. In this model, population density of levels is determined by collision. Level of population is governed by Boltzmann distribution, and the excitation of level occurs by collision. There is also a more complicated model that was supposed to supply the difficulty of other models. This model is valid for all density. However, the model is difficult to be applied. It takes account a lot of atomic process, and you should know the code are required for applications in this model. Because this model takes into account a lot of atomic process, it's very complicated to do some calculation with this model. To quantify the ionization, to quantify the intensity of spectral line, you should know coefficient rate for any different process. For example, coefficient rate for ionization, coefficient rate for recombination, d-electron recombination, excitation, and so on. For tokamaks, a coronal model can be applied to calculate the coefficient rate for ionization, and the Lotz formula can be used. For the electronic recombination, you can use the Berg's formulas. The coefficient rate for excitation, unlike model for ionization, is not possible to describe the excitation rate for wide validity. The largest, most extensive source of excitation rates can be found in the Weinstein-Sobelman-Yukoff books. It's a very complicated coefficient rate because there are a lot of processes that can be happening in the atoms. There are a lot of transitions that electron can be done in the atoms. This coefficient is very difficult to estimate. There are a lot of codes for atomic radiation, for calculation of atomic radiation in the atomic process. The most popular is the ADA codes, is the European codes. There is also Fleischek, this is a Chinese code. The very friendship code, use it to use it, easy to use it. And it's a good code for some kind of applications. The line radiation. The spectral line radiation from atoms provide a lot of information about the plasma. For example, for 50% of light and semi-heavy impurities with atomic number range 10, 6 to 26 are completely ionized for temperature described by this equation. When temperature can be described by this equation, the atoms are completely ionized. For example, for argon that has 18 electrons, for temperature higher than 5 Kev, the argon are completely ionized. For carbon, this temperature is about 120 eV. Line radiation and its measurement allow identification of elements present in the plasma column, determination of impurity flows, determination of impurity density, investigation of transport process in the plasma. The line radiation, there are some profile. The width of this profile gives us information about IO temperature, and the Doppler shift of this spectral line, if you know the wavelength of spectral line, you can calculate the Doppler shift of spectral line. This Doppler shift is related with the plasma rotation. That is a very important topic in the plasma fusion. From line intensity, you can also obtain information about impurity density. So ions with different degrees of ionization are distributed in shell-like structure. Impurities with low Z are completely ionized. Only medium and high Z elements emit radiation from the center of plasma column. Ion with noble gas configuration can exist over a wide range of temperature. Here you have ion distribution for different temperatures. You can see from this picture for low temperature, the iron are low ionized, and however for high temperature, the iron can be completely ionized. Here you have spectral profile of from argon atoms from the ASDEX machine. It can be seen from this picture, the low ionized argon are located in the plasma edge. Here you have hydrogen-like argon, helium-like argon, and so on. Excitation energy of spectrum line increase with Z square. Spectroscopy should cover a wide spectrum in wavelength. Line emission is invisible in the ultraviolet region for plasma edge, and this in soft X-ray or VUV for plasma core. Visible in the ultraviolet region of spectrum. In this region, you can use optical fiber and the normal components like glass, quartz, and so on. Diffraction grating is used or prisma to spread the spectrum. Detectors are electrophotomultiplier, photodiodes, and CCD cameras. In this part of spectrum, in general, we have good spectral resolution. Here we have some spectrum from the TCABR Tokamak for a visible region of the spectrum. In the TCABR, the most important impurities are carbon impurities. You can see a lot of carbon lines. Here you have a spectrum from the ASDEX. In vacuum ultraviolet, the light is strongly absorbed by air. Grating for diffraction can be used. Detectors occur without windows, with electrophotomultiplier and the CCD cameras. In soft X-ray, a small angle of incidence to increase the reflection of diffraction grade, slow resolution, and we use the same detector as in VUV region of spectrum. So here you have we have some spectrum from the TCABR in the vacuum ultraviolet. As can be seen from this picture, the most important impurities in the TCABR are carbon and oxygen. Another kind of information that you can obtain from the emission of spectral line is the plasma impurity density. In this kind of measurement, you compare the intensity of experimental result of intensity of a spectral line with some theoretical estimation of this radiation. To be obtained the ion impurity density with some degree of precision, you should know very well the coefficient rate for transition, for this transition. This is a complicated task because there are a lot of atomic processes that can be excited this transition. Another type of diagnostic in plasma fusion is the bolometry. Bolometry measures the total radiation of plasma. These radiation are connected with energy loss. So you use the bolometry to estimate the energy loss from the plasma. In 1970, radiation loss were considered to be less than 30% of impute power. However, measurements in GT tokamak show that the radiation can be changed from 50 to 100% of the total energy. TFTR tokamak maybe 60%, 50% in the T10, and the 50 to 85% in the PLT tokamak. So the radiation loss is a important source of loss in the tokamak. The bolometers detector are specially designed to have a flat spectral response over a wider range in wavelength. It must have their peak response in the UV region, where the most radiation can occur, and it has low temporal resolution. The more problem of this kind of detector is the temporal resolution, because in the plasma fusion, the duration of plasma is very low. In our tokamak, this duration is just about 100 milliseconds. In this type, you can measure it, the evolution of radiation. So you should have a bolometer with good temporal resolution to be analyze the dynamic of this radiation. Another kind of information that can give spectral line is the Doppler shift. Doppler shift are connected to the plasma rotation. In tokamak, plasma can rotate in the poloidal direction and in the toroidal direction. The rotation in the shear of rotation in the poloidal direction are related to the suppression of turbulence in the plasma column. In the toroidal rotation are connected to the suppression of some kind of MHD instability. However, to measure the Doppler shift of the spectral line is not so easy task. Suppose some estimation. If you have 5 kilometers per second velocity, you can estimate the Doppler shift of spectral lines that are located in the visible part of the spectrum. This Doppler shift is about 0.009 nanometers. It's very small Doppler shift, and it's very complicated to measure this Doppler shift. However, in our tokamak, we have done this kind of measurements. The first measurement of plasma rotation was done in my PhD work. Here you have the experimental setup for this kind of measurements. That was a simple method to measure the Doppler shift. Here you have an optical system that collects light from the plasma, and this light is transmitted by optical fibers to the monochromator. Here we have also a semi-transparent mirror that collects the light from the external lamp, like a neon lamp. And during the plasma discharge, we rotate the diffraction gauge to be scanned the spectral line of impurity and the spectral line of the lamp. Here, you have the temporal evolution of these two spectrum. In the red is the spectrum of neon lamp, and here in the black line, you have the spectrum obtained for position 2. In this position, Doppler shift is equal to 0, and in the position 1 is represented by a blue line. If you know very well the velocity of grating and the wavelength of the spectral line of the lamp, you can estimate the wavelength of this, the line of the impurity, and estimate the plasma rotation. So here you have some profile of plasma rotation, poloidal profile of plasma rotation, this here toroidal profile. As can be seen from this picture, the maximum velocity, poloidal velocity, is about 5 kilometers per second. It's a very low velocity. Here, the velocity is so less. However, toroidal rotation, the plasma center is about 10 times higher. It's about 20 kilometers per second. In this kind of measurements, we also observed that in the plasma edge, the rotation inverts the direction. So in the central part of plasma rotates in the opposite direction of plasma current. In the plasma edge, the rotation is in the same direction of plasma current. So after these measurements, we have done an upgrade in this diagnostic. This you have the diagnostic for temporal evolution of plasma rotation. The main idea behind this diagnostic is if you put here one detector to measure some part of spectral line, and here another detector to measure another part of the same spectral line. When light starts to move left or right, when one area increase, another decrease. Take the range of these two areas, you can obtain information about the plasma velocity, about the Doppler shifts and the plasma velocity. Here you have experimental setup for this kind of measurements. Here you have some transparent mirror that split the light for two different detectors. Here we have temporal evolution of plasma rotation in the center of plasma column. This rotation was about 20 kilometers per second for the different position of gas injection. Here now you have upgraded this diagnostic. Now we can measure it in the same time the poloidal rotation, toroidal rotation, and there is one channel I forget. For control. Mm-hmm. This diagnostic, now we are applying a project to FAPESP to increase the number of channels to 8. The main requirement for choice of optical instruments. you should take in mind when you choose any kind of instrument that is the wavelength of interest, spectral resolution, brightness of emitting source, temporal resolution, the kind of detectors, sorry. The main instruments used in spectroscopy measurements are monochromator or interferometers, filters, sorry, mirrors, optical windows, optical fiber, detects of radiation, so on. There are two types of monochromator. The most common is the Turner monochromator. And in the astronomy, when you need high spectral resolution and you have a low signal, we can use the HLA monochromator. This HLA has a little different geometry, has a diffraction rate and the prisma. Here you have a spectrum obtained with CCD camera from this Cerny-Turner monochromator, and here you have spectrum obtained with HLA monochromator. As can be seen from this picture, this monochromator gives information about the spectral range for different diffraction orders. So if you obtain the spectrum in different spectral orders, you can obtain a high precision in the spectral, good spectral resolution. The main monochromator parameters are focal distance, spectral resolution, and the linear dispersion. About detectors of radiation, the most common detectors of radiation are photodiode, avalanche photodiode, multi-pixel photo count, another kind of detector, and the photomultiplier. This detector has different quantum efficiency. The most higher is the photodiode detector. The photomultiplier has low quantum efficiency. However, the gain of this detector, the most higher gain, is obtained with use of the photomultiplier tube. This gain can be reached 10 millions. So another important part is the choose of detector. You should take care when choose your detector. There are image detector. The most common is CCD and CMOS cameras. So CMOS has better temporal resolution. However, these are more expensive detectors. CCD are two types of CCD, that is front illuminated and back illuminated. The back illuminated CCD has more quantum efficiency. Okay. Here I provide some estimation of radiation. Before you choose your detector, you should estimate how many photons you can collect from your source. Here I have done some estimation. Suppose I am interested in measuring the average charge of plasma. The average charge of plasma can be measured from the brainstorming radiation in the visible part of the spectrum. And use the TCR-BR plasma parameters. We estimated that about 7,000 photons per second per pixel. So if you are interested in 1 millisecond temporal resolution, your detector should be able to measure just 7 photons per millisecond per pixel. You should take into account the signal noise rate in this kind of detector. So you should be very careful in the choice of detectors. The most important parameter for choice of detector is the flux of photons per second of your source. If you have a slow flux of photons, you should work in the photon count region. Photon multiplier can be used in the wide range of flux photons. The PhDs is normally used when you have a higher photon flux. So about optical design, the radiation of plasma in general is very slow. It's very difficult to collect these photons. If you work with spectroscopy of thermonuclear plasma fusion, you should take into account to lose any photons. Since the radiation is very low, you should be clear in the project of your optical system to collect this light. Here we have some example. These are double Gauss lens. And the most important parameter in the optical design is the spot. The diameter of this spot is not 0, of course, because there are a lot of aberration in this optical lens. This geometry is different from 0. You should take in mind that the diameter of spot should be less than the pixel size. Here you have some example of spot in different focal distance. So the less spot is near from the focal plane. And another thing that you should be taking in mind is the transmittance of optical system, because in the plasma the emission is very low. You should be taking care with the transmittance of optical system. Suppose you have a very complex optical system like this with a lot of lens. In this system, if you try to measure plasma radiation from the tokamak with this optical system, you can be not able to receive any photons in your detector. So the transmittance is very important thing to be taken into account. Each surface in general reflects about 44%. If you have a lot of surface, this number can be about 100. So, however, applying the optical coat in this surface, you can increase the transmittance of optical system. So in our group, in our laboratory, we create the optical design group. The goal of this group is create a software bank, create a group of Brazilian designers, and intensify the collaborations. We are interested in the optical design of optical systems, aberration theory, design and optimization methods, and the tolerance of optical systems. There are a lot of optical code to design your optical system. The most popular is Optical Studio, the code Zmax, Oslo, and the code V. Thanks for your attention. So,
thank you very much,
thank you.
Professor Severo. So I will handle the questions and answers. So I will start with a question from our PhD student, Graziela Diaz. So she's wondering what is the effect of turbulence for plasma spectroscopy?
The turbulence is very complicated task in the plasma spectroscopy. The signal that you measure, there are a lot of noise. You should interpret this signal. However, this turbulence can be suppressed if you have shear of plasma rotation. To measure the plasma turbulence, there are another type of diagnostic. In general, the turbulence is measured in the plasma edge with electrical probes. There are some try to measure this turbulence with optical system. However, it's not so easy. Not so easy to measure. I had one student, magister student, that had the plasma emission, the bolometer and the X-ray emission, and we can from this emission you can be estimate the magnetic island that are in the side of plasma column, the width and the position of this island. So turbulence is a complicated task, and for spectroscopy, it's not so easy to work with this turbulence.
I would like to add one question from myself. You mentioned about the bolometers to measure to make the measurements. So how can one use bolometers to select energy range? How do you do that? With a special sensor, or you have always to integrate over all energies?
Yeah, it's a special detector. It's in general, it's a very thin. The page of detector, the gold. This detector receives particles and the photons. In general, this detector have a flat spectral response in this in the wide spectral range. So from this signal, you can estimate the loss of plasma columns. In general, when you use this kind of detector, you should calibrate this detector. The calibration is not so easy. You can calibrate this detector with, suppose you produce plasma with argon gas. Because the atomic number of argon is very high, the input energy comes through the radiation. All energy comes through the radiation. 100% input energy comes come through radiation. So you do some discharge in this gas, measure the radiation of this signal, and measure the plasma current and the loop voltage. You can obtain information about, you can calibrate this detector. This is a special kind of detector. It's very, this detector has a very low temporal resolution in general.
Okay.
The most common bolometers are photodiode bolometers. These are very, it has very high spectral resolution, but not flat spectral response.
Another question from Graciela Diaz. So she asks whether there is practical applications for the spectral lines obtained in thermonuclear plasmas. Don't know if I understood well the question. Graciela, if you want to add something, just go on.
No application for spectral line radiation. You can obtain a lot of information from this spectral line radiation. Ion temperature, electron temperature, plasma rotation, and ion impurity density, and so on. Line radiation gives us a lot of information about this plasma.
Alison, can I just add some information about my question? Hi, Dr. Severo. I just asked this question because I know a bit about synchrotron. I mean, the one we have in Campinas, that they produce some special spectral lines to deal with. I mean, there is some application of the for these spectral lines with some I don't know if I can explain that, but with this, oh, you can go ahead. Sorry.
Okay, I understand your question. The cyclotron radiation in the plasma, not you can obtain the cyclotron radiation in this plasma. You should have electrons with higher energy. It's most common in the accelerators. The plasma, the radiation don't reach this part of spectrum because the electron has the thermal energy that should be about 10,000 eV. The energy of electron is very low. To obtain this radiation, you should accelerate this electron for a long time. The radiation can be reached this kind of, you can obtain this kind of radiation with acceleration.
Okay, yeah, thank you.
Elder, may I ask a question?
Okay.
I understand that one problem is to measure simultaneously several wavelengths, no? For example, to estimate the Doppler velocity. So ideally, you as much wavelengths as you are able to sample simultaneously, better, no?
Yes, this kind of diagnostic to measure plasma rotation, you not use the CCD cameras. With CCD cameras, you can measure a lot of spectral lines in the same time. However, this CCD cameras has very low temporal resolution. We measure the plasma rotation with a photomultiplier detector. So you measure just one spectral line at the same time. If I interested in measure the plasma rotation in another position of plasma column, and I know that in this position that ion, you cannot find this ion in this position, you should take another spectral line to measure the plasma rotation in another position. So you can use a lot of spectral line to infer the plasma rotation, but in time you measure only one spectral line.
I see. But in your updated setup, you are trying to measure two now.
Okay. Sorry. True. So you can show again this experimental setup.
Yeah, I think in the updated one. Yeah, this what.
I'm not sorry. Yes, here.
So here you can measure simultaneously two wavelengths, no?
Yeah. Yes. because the rotation of diffraction gauge scan the spectrum of this spectral line. In the time when discharge occur, you produce a rotation of diffraction gauge, and this rotation scan different wavelengths. Of course, in the scan of this wavelength is done in different time. While we in this measurement, we suppose that the Doppler shift not change in this interval. And not in this measurement, when you measure the temporal evolution, you can be see in the plateau region, the velocity is very is constant in this. So you can this was the first measurement of plasma rotation in our laboratory. When I begin my PhD, you had a CCD camera. This CCD cameras broke down, and I should invent another method to estimate the Doppler shift. And our possibility is just to measure by rotation of diffraction grade. This work I present in the conference in 2003 in the France, in the energy EIA energy conference. The referee when this methodic did not accept this work. However, in 2027, the nuclear fusion published one special paper about our unknown that was acquired at the time. This was the only Brazilian paper that was included in this review. So,
and what about Zeeman effects? Have you ever tried to measure during this time?
Yes, there is a Zeeman effect in the plasma. However, in our laboratory, you can estimate these Zeeman effects. There are another kind of diagnostic that measure the Stark effect. Stark effect give us important information about the radial electric field. Stark effect. Zeeman effect, I'm not sure that there are some kind of diagnostic that can be used to measure some plasma parameters, mean hide the Z effect.
There's another question from Valdemar Bellintani. Can we get results from other impurities like oxygen?
Yes, it's not a good question. It's a good question. However, the most important impurity that there is in our tokamak is the carbon impurity. Our limiter is from graphite. The most common impurity are carbon impurity. You have oxygen impurity in this tokamak. However, the intensity of this spectral line in the visible part of spectrum is very low, and you cannot able to measure oxygen line in our tokamak.
Okay.
I'm curious about for one operational tokamak. How do you intend to collect the energy?
In general, in reactor.
In a reactor,
How
operational
one.
one.
Energy. Mm-hmm.
Okay. Energy comes, the energy of neutrons comes from the mass difference that is transforming in energy. This kinetic energy of neutron should be absorbed from the plasma, from the reactor wall. This neutron should be absorbed by this wall, and this produces a heat, like a fission reactor. This reactor should be work very similar with fission reactor. These neutrons hit the plasma, the tokamak wall, produce a heat, and there is a closed circuit with water that absorbs this heat and it transmits to another circuit that produce this water can be rotated the generator, electrical generator. Indeed. It's very similar with a fission reactor, the principle of work.
I guess you have also
how far away are we from having an operational fusion reactor?
This is very far away. Now is being built the most large tokamak in the world, that is called ITER. It's a big machine. It has a major range about more than 60 meters, minor range about 2 meters. Plasma current should be about 15 million amperes. This is an experimental reactor. This reactor should be able to start work in the 2024. Yes, 2024. Should be work for 10 years. After that, you should done another reactor which will produce the electrical energy. This reactor that are being built in the France now is not to produce energy. The experimental reactor. Another generation, this reactor should be produce energy, but it's a very expensive reactor. Very expensive reactor.
Luis, you had a question?
Many questions. One that I'm wondering, what limits the time window for the discharge magnetohydrodynamic instabilities? What is the duration of what limits the duration of the discharge?
Duration of discharge in our tokamak is about 100 milliseconds. This duration is different for different tokamak. In our tokamak, this duration is about 100 milliseconds. The magnetic oscillation that has a frequency about 15 kilohertz. So the kind of turbulence and the oscillation that you have in the plasma.
So this turbulation limits the duration of the discharge, no?
Yes. This turbulence can produce a lot of I don't know, a lot of problem in the plasma discharge. You lost energy by the turbulence energy and the particles. There are loss of particle and the energy generated by this turbulence. And there are most important turbulence is produced by M2 mode M2 mode can finish the charge. The explosive mode is a magnetic island that is increasing the time in the plasma column, and after some size of this magnetic island, the plasma can finish very happy. It's a very change disruption in the plasma column.
I see. Well, that's very nice notes.
Mm-hmm.
Okay, there are no more questions. So over to you, Luis. Luis?
Wait, hi.
We don't have more questions, so it's with you now.
Okay. Would you like to close, Alison?
Okay, so I can do the closing. You have something else to say, Dr. Severo?
Thank you very much for the opportunity. It's a pleasure for me present my work to you, and thank you very much for the opportunity.
So on behalf of INPE and on the Space Geophysics postgraduate program and on the Research in Heliophysics project sponsored by CAPES, I would like to thank Dr. Severo once again for presenting this very interesting seminar. And I would like to thank the audience for staying with us. And this presentation is recorded and will be available for those who are interested in watching it again. So once again, thank you very much, and thank everybody.
Thank you. Thank you.
Thank you very much, Leon.
Mm-hmm.
So I will close here. Bye.